Okay, thank you for coming. My name is Heinänen. I'm covering my colleague Dr. Antti Helminen, who was not able to be at this conference and exhibition. And I'll be talking about improving mmWave radar performance with ultra-low loss PREPERM materials. These can be also applied to any material selection. The reason I'm talking about PREPERM is just to give you an overview of the possibilities to use our materials. Okay, so as all of you know or should know or will know, there's quite a lot of mmWave applications out there already, and the amount of them are increasing. Yeah, I drew this myself. And the applications vary from communications device, point-to-point antennas, 5Gs using most probably mmWaves, automotive radars, weather radars, these kind of security scanners, gesture recognition in mobile phones, etc. And something to take into consideration in these applications is, of course, the low loss or the low signal loss as possible via correct material selection. And something to also take into consideration is the very wide range of different weather or environmental situations. It might be very hot, very cold, snowy, rainy or foggy. There might be quite a lot of water or humidity near the, for example, radomes of the antenna and so on. And these are something that you always have to take into consideration when choosing the materials. And first, a few words about PREPERM, what it is, and why do we have it, and why should you use it, and how should you approach as when you want to use it. So it's a thermoplastic material, not a thermoset. So basically it's a plastic that can be injection molded, so very efficient in mass producing many pieces and so on. And it's especially designed for RF or increasing your RF performance via low loss. Whether it's very low dielectric constant or very high dielectric constant or permittivity that you are using. And when you are using any kind of material, it's one thing to have the characterization in 100 megahertz, and it's just very different in 100 gigahertz. So that's why we have, for example, characterized variety of our materials in low frequencies as well as high frequencies, even up to 220 gigahertz. And what we always do is we start with our standard grades, and then we tailor the plastics for the customers so that it best fits their needs. If it's something that has to have mechanical properties of something, and then you can compromise in some other features, then we can always tailor-make the material so that it best fits the need or the design that you have. So you don't have to design around the plastic. You use your own design, and then we provide the best plastic to fit your need. Few words about the material performance. This is basic slide that we always show. So these are measured at 1 gigahertz. In the x-axis there is the dielectric constant, and we are able to tailor it from 2.55 all the way up to 22, 23, and now a few weeks ago my colleague just made a new test product with dielectric constant of 27. Imagine that. A plastic with dielectric constant 27. And we always try to make our plastics so that they are very low loss. We don't want to make any compromises on the signal attenuation on the performance of the antennas. And this is the base material that we have characterized up to 220 gigahertz. And the orange dots you see there, they should be somewhere around the 2.55 dielectric constant range over the whole spectrum of this graph, and it's quite stable. I challenge any other plastic provider to show this kind of similar graph that the dielectric constant is stable at very different frequency areas, as well as looking at the purple dots. That is the dissipation factor. So if you're looking at 1 gigahertz, our dissipation factor is 0.0005, and increasing the frequency 100-fold to around 100 gigahertz, it's 0.005. So only 10 times higher than where we started from, even though the frequency is 100 times higher. So very stable. And something about the environmental data. Earlier today I discussed about different designs at our stand that are working in very varying temperature ranges. These are the standard telecom temperature range, -40 to +85. And I have seen graphs of different materials that are linear, non-linear, and so on. And these are something that I'm very happy with to show to any customer or you guys here. And even though this dielectric constant 9, the L900 HF grade, even though it looks it's dropping heavily, it's only a few % off of the spec. And then when you're designing, for example, automotive radars or any kind of radomes, you always have to take into consideration the weather conditions. This is actual data where we have shown or measured the water absorption of different materials under immersion. So we put them into water, not only humidity from the air, but into water. And compared to many other materials, you have to be sure in your designs that you don't lose any radar power or signal power due to environmental issues. This PEI is also known as ULTEM. The reason why we did this kind of under immersion study is because we have difficulties detecting humidity absorption from air because it is so small. And that's something that's surprised our customers from year on to year. And something that when you're doing your antenna designs or radome designs, you have to be sure that the dielectric constant is very stable across the different pieces. This is a 10 by 10 centimeter plaque that I measured myself at the lab, and the spec for L440 is dielectric constant of 4.4, and it is very isotropic over the different measurement points. And when you're designing your antennas, you should always be very confident about your raw materials so that it's very isotropic or there is no anisotropic issues with it. Also that it is very homogeneous in each of the raw material bags, for example, as well as from batch to batch. So if you order 1,000 kilos today and 1,000 kilos next week, it always has to be the same. or within very small tolerance. And this is actual production data out of our own factory. And it varies a little, of course, because it's engineering. It's not natural sciences, which has to be very specific. So if you think about having about 2% tolerance of what we promise inherently, that's quite good. And now something that I think that you've all come here to hear are the customer cases, and I'm going to talk shortly of 3 different customer cases. One is weather radar that's been that uses millimeter waves. One is a security scanner that uses millimeter waves, and one is an automotive radar. So this is one German customer who is very happy with our material, and they use PREPERM in the lens of their radar to make a very, very sharp and precise beam that they use to analyze the rain droplet speed and direction and size distribution from the reflections. And with that they are able to tell the authorities, or the authorities are able to estimate what is the rain amount in different areas, and then use that to help traffic control. And why they chose us is the uniformity within batch as well as batch to batch, as well as the temperature stability, and also the minimal water absorption. Because if it's raining, you have to be sure that the water doesn't compromise the signal. And here is the security scanner. So basically, they are using millimeter waves to scan you at the airport, for example, or train stations or wherever. And they had a very poor image quality due to very high losses in the radome, or the antenna cover. And what they did was that they contacted us. We discussed with them what is their needs, what kind of technical characteristics they have to have in the, or the properties that they have to have in the plastic. Then we designed it only for them and supplied them these kind of ready-made sheets so that they only have to implement them into the construction. And they were very happy. As you can see, the image quality is quite different between the before and after pictures. And the final case, automotive radar, because of different or parameters, you have to optimize what you are coming to compromise with. For example, the earlier plastics that are being used in automotive radars is, for example, PEI and PBT with glass fibers. And when designing, for example, a radome, you have to take into consideration the isotropy, the repeatability of the dielectric constant, the loss factors, what kind of dielectric constant do you have to minimize the S11 reflections, or the S11, what is the dimensional repeatability in the injection molding, and so on. And as you can see in the orange, we are not best at everything. I'm a different sales guy. I sell the truth and not bullshit. And here's something that we did in-house with a 24 gigahertz radar. On the left, you can see the received power in dB of air, only air. Then we included this around 3.3 millimeter radome in front of the radar and simulated that as an antenna cover, and then moved it few millimeters by few millimeters to achieve this graph. And we did the same with PVD with glass fibers. And the difference is quite shocking, how much you lose by choosing the wrong material, or vice versa, how much you gain by choosing the right material. And one curiosity from this picture on the right is that it was actually the thickness of the radome was very close to optimal for the PBT and not to our material. So we lost a few fractions of dBs because of the thickness of the radome. Okay, so summary slide, still on time. Basically, you know that the millimeter wave radars and devices and communication equipments are increasing heavily. You have to have very good material to not compromise your design, or just to keep the customer happy. One way of putting it. And you have to design it so that, or be sure that it works in hot and cold and rainy and even wet conditions. And you have to be sure that it works always. And our material is developed especially for these kinds of applications as well, and we have several different products for different applications, and we're always pushing the boundaries and making better best fit solutions for our customers. Thank you for your time. We have few minutes for questions, and if we don't have enough time here, please come to our booth 193. Let's have a good discussion. We also have samples there that we can show you to get your head around what kind of designs are possible with injection molding, not only planar, but also 3D shapes. And okay, we are here for the few days, and please have few times for questions. Languages preferred are English and Finnish.
You provide the specs, we deliver the solution.